Okay. All right, my name is Bill Schlatter. I'm an instrument scientist here at the LCLS, which stands for LINAC Coherent Light Source.
My name is Sam Webb. I'm a staff scientist at SSRL.
So my name is Keith Bechtel. I'm a graduate student at Stanford, but I work here at SLAC.
I'm the director of SLAC National Accelerator Laboratory. We're standing in front of my administrative building on the central quad of the laboratory, which is where the science gets done. SLAC has a mission to deliver outstanding science to the nation in areas of what we call photon science, where we use X-rays to probe matter at the atomic level, on atomic scales of time and energy and position. And we also do the science of particle physics and particle astrophysics, where we're asking, what is the universe made of at its most basic and fundamental level? How did the universe begin? How will the universe end?
SLAC is the SLAC National Accelerator Laboratory. It's a Department of Energy, basic energy science laboratory. And so we study all sorts of things here, from proteins and crystals to materials like superconductors. But we also have, there's work in particle physics, particle astrophysics. And most of all, we work on building accelerators here. So there's a lot of work in building particle accelerators at SLAC. That's why it's one of the two Department of Energy accelerator laboratories.
And SSRL is a user facility where we use accelerators to produce very intense X-rays. And we use X-rays as a probe of all types of materials. They can be biological materials, environmental materials, or man-made materials like in batteries and energy research. We then, the X-rays are an ideal wavelength to probe the structure of these types of materials. And so we do all sorts of different experiments that probe the properties, both chemistry and structural, of these materials.
Today the accelerator is actually used as an X-ray laser. So it's pretty simple. You know what a laser is, you know what X-rays are, and you put them together and now we have an X-ray laser. So it's basically a very large laser that generates X-rays.
Well, I think when most people think of SLAC, they think of a 2-mile-long electron accelerator that was built starting almost 50 years ago to ask questions about what is the world made of at its most basic fundamental level? What is the smallest building block of nature? And using that 2-mile-long electron accelerator, the quarks, the basic building blocks of all the matter we see around us, they were discovered there. But as time has passed, this laboratory has evolved, the frontiers of science have evolved. And in terms of particle physics, we've gone way beyond those initial experiments, and we now look out into space to ask questions about what are the dark matter and dark energy made of that make up 96% of the universe. And we're using that same electron accelerator to make the world's first X-ray free electron laser. I spent most of my life in the last year in Washington walking the halls, talking to Congress people, explaining to them the importance of investments in basic research. There are areas of science where the basic research we do today is what will deliver the economic competitiveness in the decades to come. You have to take a very long view because it's like an investment portfolio. There are some things we can do now that maybe delivers new results in 5 years, but the kind of science we're doing with our X-ray laser here, that has the potential to do fundamental basic research on a process like photosynthesis, where for the first time we're going to be able to actually see photosynthesis step by step because we have the ability to see things happening on the time scale that exciting stuff is going on, such as the multi-step photosynthetic process. We can, you could imagine, make a movie of it with sufficient resolution to see the intermediate steps. Once we understand something like photosynthesis, there's a chance we can control it. So we want to see it, understand it, control it.